Hello again, Calc BC, and welcome to another video lesson. Today's lesson, we're going to be focusing on a very important idea for us, continuity of a function. And you know, many of our formulas, theorems, things that we employ rely heavily on the continuity of a function. So we'll start off by defining continuity one more time. I know that's a bit of a review. And then we'll talk about what we really mean when we talk about continuity, which is where is it not continuous? Where does the function have discontinuity? And then we'll take a look at a couple of the ways that we might show continuity. There's one in particular that has to do with differentiability that is really important, and so I want to make sure we hit that today. So we'll start off by talking about continuity at a single point. Then we'll talk about continuity on intervals. So continuity, at a point. Okay, so what we'll say is that, you know, the function f of x is continuous at a point. We'll call it C, if the following three, oh my, nice typing, following three conditions are true. One, two, three. Right, and so you probably remember these from AB, but just we want to make sure that we review them. The first condition, as you probably remember, is that the limit as x approaches c of f of x must exist. Okay, so right away, then what that does is launches us into the conversation. Okay, so how do we know when limits don't exist? And you know, there were three possibilities where they don't exist, right? Uh-oh, I can't write up there. Ha! It's not letting me write at the very top. I'm not sure why. It must be getting close to the screen up there. All right, so I'll write it over here. Limits do not exist. Oh, now it's letting me right there. Okay, so there were three conditions. One of the conditions was unbounded behavior. So the limit as x approaches c is infinity or negative infinity. So that's unbounded behavior. That limit doesn't exist. There's the left and right hand limits fail to agree. Left and right do not agree. And the weird one was that third one. It's pretty specific to like trig functions, but it's the oscillator with increasing frequency. So I always like to use like cosine or sine of 1 over x as an example. As you get close to 0, that function just starts to oscillate really, really fast, and there's no way to nail down where that function or where that limit is actually approaching. So, all right. So the limit must exist. F of c must be defined. Okay, so obviously, and we're talking real numbers, so no square roots of negatives, no division by 0, that sort of thing. Obviously, division by 0 would also be unbounded, but hey, that's all right. So we have to know that f of c is defined. And thirdly, that limit as x approaches c of f of x needs to be f of c. So, you know, there's none of this where, you know, you're approaching and then there's a hole and there's a dot somewhere else on that vertical line at c. It has to equal f of c. So those were the three conditions that were true for continuity at a single point. Then we went into some graphical examples where we could break various parts of those continuity conditions. So I will just draw a few of them here. There's certainly by no means an exhaustive list here. You know, first thing I like to draw is when the limit doesn't exist. So, you know, maybe you're thinking about the old, you know, absolute value of x over x, right? Where, you know, f of x is absolute value of x over x. Oops. Because, you know, that's either positive 1 or negative 1. But as you approach 0, you know, this function is not continuous there at x equals 0. Okay, so you know, we know what these all look like, so I'm not going to belabor the point too much. You know, one where the limit, where the limit exists, you know, but it's not equal to the function value. So something like my typical function that I like to draw, it's got a hole in it, right? So here's C, and f of C is actually up here, right there. So as we approach left and right, f of C exists. There's a limit. We'll call it L. Sure, no problem. But the problem is the function value at C is different than the limit, so that function not continuous. All right, I'm not going to belabor that too much. Just so that we have a you know, kind of mentally, you know, refreshing ourselves in terms of what continuity means. Then we had continuity on an interval, and we had two types. Okay, so continuity on an open interval, that was easy. F of x is continuous on the open interval a to b if f of x is continuous for all c in the interval a to b. Easy. Okay, yeah, just make sure it's continuous for all the points in between. Now, really what we do, right, is we make sure that none of the discontinuities are in the interval a to b. Piece of cake. Okay. The harder one, or the more technical one or involved one, was continuity on a closed interval. Okay, because we ran into a problem. Right? F of x is continuous on the closed interval a to b if f of x is continuous on the open interval a to b and okay, and then this is where we ran into the issue, right? Because at the endpoints a and b, we don't have limits. Okay, we have one-sided limits only, and so we had to ensure that that the left-hand side, so at a, that the limit as x approaches a from the right is equal to f of a, and the limit as x approaches b from the left of f of x is equal to f of b. And it's sort of inherent in there is an implication that f of b and f of a are both defined. So yeah, so this brought us to the idea of that one-side limit, and this was sort of the first time we saw it. No, actually, sorry, second time we saw it, because when we defined limits that don't exist, we looked at it, how from the left and the right they had to approach the same thing, but we didn't really call it limit left, limit right until then. So yeah, for continuity on closed interval, we have the added requirement that the one-sided limits equal the endpoints. And why is it one-sided? Because when we close the interval, we basically stop the universe. The smallest value we have possible is a. So you can't approach a from the left. Similarly, on the right-hand side, you can't approach b from the right because there's no values bigger than b. So there's our review of continuity on both open and closed intervals. Now, the reason that all these things are important is because a lot of the theorems that we use in calculus require continuity. Okay, so if you think of any of the theorems that you can remember, intermediate value theorem, function has to be continuous on the interval. Rolle's theorem, mean value theorem, fundamental theorem of calculus, they all require continuity of a function. And sometimes people tend to gloss over the beginning parts of theorems. Like when we write out the mean value theorem, for example, it starts out with, say, let f be a function that is continuous on the closed interval a to b and differentiable on the open interval a to b. Okay, and that's an important part of the theorem, because if either of those is broken, then the theorem doesn't work. Okay, and so making sure that you understand that continuity is a big deal, differentiability is a big deal, is really crucial in our justification work in Calc BC. And it was really obvious on last year's BC exam, the students that truly paid attention to that, okay? Because there's one really important thing that College Board wants you to remember, that differentiability implies continuity. This was a huge idea on the BC test, because I had lots of students, very smart students, okay, screw this up. And it was on there multiple times. You see, if you're going to invoke the intermediate value theorem to prove why there's a zero in an interval, let's say, okay, so I know that the function is, let's say I know the function is negative here. Oop, that's not a point, that's a line. Get rid of that. I know the function is negative here, and I know it's positive here, okay? And I know that the function f is, I forgot to label these, sorry. This is A, this is B. F is differentiable on open interval A to B. So does F have to have a zero in the interval A to B? The answer is yes, it does. But why? The intermediate value theorem. The intermediate value theorem doesn't say anything about differentiability. It says as long as F is continuous. See, no matter what I do, I can't draw a line and get from A to B without crossing the x-axis if I draw a continuous function, okay? Has nothing to do with the differentiability of the function. What you needed to say was, okay, I know F is differentiable on A to B, therefore, F is also continuous on AB. And we could worry about the endpoints later. We don't really care about that. Actually, let's put rounded brackets in there because we're looking for zeros, and we know A is negative and F of A is negative, F of B is positive. And it was, you had to draw that connection explicitly. You had to say how you knew F was continuous. And it was because differentiability implies continuity. This is a one-way implication, by the way. It's an if-then statement. It's not one of those, you know, in geometry when you learn the if with two F's, right? If and only ifs. Yeah, continuity doesn't mean it's differentiable. We can draw a continuous function that's not differentiable on the interval. Okay, what we need is to draw the connection for your grader that differentiability means I know it's continuous. And guys, when they say F is a twice differentiable function, then you know that F is continuous and F prime is continuous, okay, because it has two derivatives. And that was a very big deal on the College Board exam this last time around. And it really bit some kids in the behind there on their scores, unfortunately. It cost them probably could have cost them up to 2 points. So instead of a 5, they got 3s. Yeah, it was a pretty big hit. Okay, so that's it for today, I believe. If not, I will edit this and add some more so you'll never know that this happened. So anyway, hopefully you guys had a great weekend or are having a great weekend and get a chance to watch this video. Have some notes now that really help narrow down or nail down for you your definition of different or continuity and the important impact it has on our functions. Have a great day, everybody, and I will hopefully see you all in class soon. All right.